Okay, class, welcome to the last lecture that we are going to have in regards to the general chemistry equilibrium chapter. So this final lesson is going to be on equilibrium concentration calculations. So the calculations that we've done so far have really been involving Kc and the equilibrium constant. This is going to go into some more detail where we already know the equilibrium constant and we would like to predict what the concentration of the products and reactants will be at the time of equilibrium. And we only know the initial starting concentrations. Okay, so if we know the equilibrium constant for a particular reaction, we can calculate those concentrations in the equilibrium mixture. And we get that from the initial concentrations. Now, depending on the information that's given and the way that the problem is set up, it can go from being very straightforward, and we'll look at an example like that, to somewhat complex, where we're actually going to need to break out the quadratic equation in order to properly solve for the variable that's going to be used for calculating concentrations. So, because this is almost all exclusively math, and we don't need to talk about a whole lot of theory in this part of the chapter, I figured I would just cut out the PowerPoints because there's no real need for them, and just head directly to the whiteboard. So, I want to start off with a more simplistic and generic example, and then we'll take a look at one that's more complicated. So let's say that we have reactant Y, and it is in equilibrium with product Z. And we're told that the equilibrium constant for this reaction is 24 degrees at 200 degrees Celsius. Okay, so it's, I shouldn't have said degrees for 24. It's 24 at 200 degrees Celsius. All right, now at the start of this reaction, we are told that Y, the initial concentration of Y, is going to be 0.850 molarity. And Z, again, this is at the onset or the initial starting point, Z is going to be 0 because we have not started this reaction. So we allow the reaction to start, and the question then becomes, once this reaction hits equilibrium and Kc is achieved, what will be the concentration of Y and what will be the concentration of Z at that point? So what this right here is QC at time 0. So the very beginning of the reaction. And remember, the reaction quotient is the lead up to the actual state of equilibrium where we finally get the equilibrium constant. So what we do is we set up something that's known as an ICE calculation. Now, ICE is an abbreviation, and it stands for initial, meaning the initial concentrations that we're going to be working with, which was given in the problem, the change, and the change is always going to be a general change, and then the equilibrium. And we'll walk through this so that each individual part makes sense. Right? So if you take a look at this, we're going to have Y and Z. Now, the initial for Y is given as 0.850 molarity, and the initial concentration of Z is 0. So that's nothing special. We've already found that from the problem. The change is that we're going to lose some amount of Y. Now, we don't know how much that is at the moment. So what we do is we put a placeholder in here and we say we're going to lose some amount, and we'll just call that X for a general variable while we're solving and doing algebra. Now, if I lose a certain amount of X, then I have to gain that amount of X over here. And it's very important that you pay attention to your stoichiometric coefficients here. So if, for instance, this was 2Z and not just Z, then it would be plus 2X when you're doing this. So I just want to point that out because in this problem, we end up having a 1-to-1 ratio. But as always, we have to be paying attention to our stoichiometric ratios here because they are important when we deal with equilibrium. So then we find out what we have at equilibrium. Well, at equilibrium, we started with 0.850, and we've lost some amount x. So we can say at equilibrium, y's molarity will be 0.850 minus x. We're going to have to solve for x. And then, of course, z, 0 plus x, is just going to be x. So that is the setup for the, you can call it an ice table, an ice box, an ice equation, whatever you want. But it is very important that you get in a habit of learning how to set up these ice tables here. Now, once I have this, the next step is to actually start utilizing Kc and set up the equilibrium in relation to the values that I just put here at equilibrium. So now Kc is going to be equal to, let's just state it at first in the general sense, z, because z was the product, over y. So that's how we would define the equilibrium constant. Now we can do one better than that, because we know that Kc is equal to 24.0 at 200 degrees Celsius. And if I fill this in, we determined that z from the ice table is going to be simply x, so I can put x up here. And then down here, I'm going to have whatever y was, and we determined that y would be 0.850 minus x. So all that's really left is I have to do some algebra. I'm going to have to multiply each side by 0.850 minus x. When that comes over here, you're going to distribute the 24 by multiplying it through to both minus x as well as the 0.850. And then you simply need to solve for x. So I would encourage you to do that and then unpause the video. So if you have successfully calculated it, you're going to find that x is equal to 0.816. Now this is not necessarily the answer. This is what x is. So what we need to find are the concentrations at equilibrium. So we're going to take x and plug it back in to both of these. So at equilibrium, the concentration of y is going to be equal to 0.85 minus 0.816, because we said it would be minus x now that we have x. Okay, so x is really representing that change factor that is going to occur between point start and point equilibrium. So if I take the difference here for these two, I end up with y having a equilibrium concentration of 0.034 molarity. All right, and then if I continue, z at equilibrium is just equal to x according to the ice chart. So z is going to be simply 0.816 molarity, because that's what x is. And now I have a concentration of z and a concentration of y at equilibrium at 200 degrees Celsius. Because remember, that Kc value can change, and therefore these values can change based on the temperature setting that we're at. That was in last lecture for Le Chatelier's principle and what affects equilibrium. All right, so just to recap the steps here before we break out into a slightly more difficult equation. Step number 1 that you want to observe is to set up your ice table. So your ice calculation, whatever you want to call it, you need to set that up and get your values in there. Okay, once you have your ice, you're going to set your Kc equal to the ice, and specifically the equilibrium portion of the ice, x values. Okay, so when you go up to your ice table, the equilibrium part, you want to grab these values, whatever you determine they are for everything in the reaction, and those are what you're going to plug into Kc. as your placeholders. Okay? And then obviously the last step, once we get there, we need to solve for x. And don't forget, once we solve for x, we then need to use it to find, I'm just going to abbreviate here, equilibrium concentrations. So remember, don't stop short at just x. When you solve for x, that is the variable of change that needs to be plugged back in to the equilibrium concentrations from your ice chart in order to actually find those values. All right, so I'm going to go ahead and clear the whiteboard here, and we're going to go through one more problem. This one will be a little more advanced. So give me 1 second to clear the board here. All right, so here's the next solution that we want to find. And this comes directly from the OpenStax textbook. We have phosphorus pentachloride gas in equilibrium with the two products that we see here, phosphorus trichloride gas and chlorine gas. Right now, in this particular situation, at the temperature this is currently running at, the Kc is equal to 0.0211. So we have our equilibrium constant. And the PCl5 is going to have an initial concentration of 1 molarity at time 0. So what our job is going to be is to find the concentrations at time equilibrium for both the products and reactants. So what we do, step 1, let's set up our ice. Okay, so again, initial change equilibrium. So initial for the phosphorus pentachloride is going to be 1.00. Okay, and it would be 0 for both of the reactants at time 0. Right now, the change is going to be that we lose some amount x, we gain some amount x, gain some amount x over here. So at equilibrium, we're going to have 1 minus x, and then we'll have x, we'll have x. Okay, again, remember, if you had different stoichiometric ratios, you could have things such as minus 2x or plus 3x, etc. All right, so we have our ice set up. Now we want to set up Kc. So Kc is going to be equal to 0.0211, and we will set that equal to the variables that we have in the equilibrium portion of the ice chart. So let's go ahead and do that. 0.0211 is going to be equal to, now it's products over reactants. We had two products here, both of which are represented as x at equilibrium. So I have x multiplied by x, so I'm going to end up with an x squared. Now, if you know your algebra, you're probably going to start realizing quickly that this is going to be a problem in terms of simple math solving. So what we have at the bottom here then is going to be the concentration of 1 minus x. Okay, so that's equal to the Kc value. So as I start to rearrange this, I can multiply through by the 1 minus x, like I did last time. But the problem is when I have x times x, that gives me x squared. And x squared is not the same thing as x. Okay? And I cannot just take the square root, because then I cannot take the square root of just singular x over here and try to work with that. So the easiest thing to do in a case like this is to use the quadratic formula. All right, so to rearrange this a little bit just so people can see it, all right, I would have 0.0211, okay, and that would be distributed to 1 minus x equals x squared. So this is what I'm working with. Now when you get ready to set something up as a quadratic equation, you want to isolate everything to one side and set the other side equal to 0. So what we would do is we would go through, manipulate this, and end up dragging all of it over and setting it to 0. So for instance, the 0.0211 times negative x, that's going to be minus 0.0211x on this side. So it would become plus 0.0211x when we move it over here. All right, so take a moment, see if you can algebraically rearrange this equation. I'll write it out down here. So what it would end up as is x squared plus 0.0211x minus, because this would have been a positive value when you multiply by 1, and we're moving it to the other side, 0.0211 equals 0. So now, if we're going to use the quadratic formula to solve for this, you have to keep in mind that we have a, b, and c. So a is an implied value in front of the x squared. In this case, it's a 1. And then b is going to be positive 0.0211. And then c is going to be negative 0.0211. Okay, these values right here. And we're looking at it, the way you would solve a quadratic formula is, right, a is in front of x squared, okay, plus b is in front of x, okay, minus c equals 0. So we've got a, b, and c, and then you've got your x squared and your x. So that's where we're going with this. All right. Now, you have to actually use the quadratic formula, and the quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is something that you are pulling out from high school math. A lot of people sing like a nursery song or something like that that rhymes with the quadratic formula. I was always taught with row, row your boat. But whatever, whether you memorize it or you have some technique to bring it up, this is something that's important that you'll need to know here. All right, so now comes the more complicated math. Now what we're going to be doing is filling in the values as I go along here. So I'm not going to keep scrolling up, back and forth, but keep in mind we already labeled A, B, and C. All right, so what I have here is negative B, and if it's negative B, it would be negative 0.021, because B by itself is just positive 0.021, plus or minus the square root of B squared. So let's go ahead and write it all out first. Okay, 0.0211 squared minus 4. Now we said A is just going to be 1 in front of that x squared, and then C is a negative because it's minus 0.0211. And then that's all over, all of this is over 2a, and a is 1. So it'll just be over 2. All right, so put that together. You should have your scientific calculator out because we're doing this sort of math. So let's start simplifying this. X is going to be equal to negative 0.0211 plus or minus. Okay, now let's make this a little cleaner in here. Okay, you should end up with 4.45 times 10 to the negative 4th plus 8.44 times 10 to the negative 2nd. Okay, and this became plus because you had a minus in here. So when you multiply 4 times 1 times a negative number, you get a negative number. And a minus make a plus in arithmetic. And that's where that plus is coming from. So let's not get confused with that. Okay, and again, this is all over 2. So I'm trying to do this stepwise so that everybody can see the individual steps as we're going along here. So let's reduce it further. Okay, solve for what's under your square root, and you should come up with this. Negative 0.0211 plus or minus, when I did this I got 0.291, which the book confirmed. Okay, and then divided by 2. And at this point, you can branch off because it's getting simple enough. So we'll get a value if we use the plus, because it's plus or minus here, and we'll get a value if we attempt the path that uses the minus. Okay, so plus or minus. Now, when you solve for these, this is solving for x. Don't forget that x is over here. So taking the positive route, x becomes 0.135. And taking the negative route, x becomes negative 0.156. Now here's what you have to do. You have to pause for a moment and think, okay, what actually is going to make sense here? Well, x is a variable that's going to get plugged in for concentrations. We cannot have negative concentrations. That doesn't make any sense. So this one is out. And that means that the x we're looking for that we want to use is 0.135. So that will be the x. I will put a note up here just so we can utilize that moving forward. That will be the x that we use to wrap up here. So don't forget, after all of this work, we have not addressed what the initial question was asking, which is what are the concentrations at equilibrium? We have solved for the change variable x. We need to now go back and plug that in so that we can actually solve it. So we are 90% of the way there, but it's very common, especially after doing a quadratic equation, you're so mentally drained from going through all the math that you forget to take that final step and plug it back in. All right, so there were 3 things that we needed to find the concentration for. The first was the reactant, PCl5. Okay, now PCl5 started at 1 molarity, and at equilibrium we said it would be 1 minus x. Well, x is 0.135. So if you take 0.135 from 1, then you're going to end up with 0.87 molarity. So that is one of our 3 answers. Okay, now the other 2 are simple. We have the phosphorus trichloride, okay, and we also have the chlorine gas. Now, if you scroll way back up to our ice, at equilibrium we said they would each be equal to x. So I come down here and I say that each of these is just simply equal to our x value, which is 0.135, 0.135. Okay. Now again, I'm just doing this as a reminder. Let's say that one of these was actually a change of 2x instead of just x at equilibrium. So for instance, if we said that was Cl2. So if Cl2 was a change of 2x, then that means when I get ready to calculate this, okay, Cl2 would be equal to 2 times the value of 0.135. Now that's not the case here, but if you come across an example like that, you need to remember to include your stoichiometric coefficients as we go through this. Alright, so I think I'm going to stop it there as far as examples. We'll certainly do more in class, but this is already going on to a 23-minute lecture, which is more than enough for these calculations. So hopefully everybody was able to understand this. Certainly take advantage of the fact that this is a walkthrough on YouTube. You can pause it, rewind it, look at it, but this should have helped break down this process into some more finite detail. As always, if you have questions, you're welcome to leave comments on the YouTube channel here for the class, or you can ask them in class and they'll come up organically as we start practicing together. So other than that, I'm going to bring our Chapter 13 equilibrium discussions to a close as far as YouTube lectures here, and we will get ready to start preparing for the new path, which is going to be acid and base equilibrium. So we're still going to be on the agenda of equilibrium, but now we're going to get very specific about acids and bases, which is its own sort of format. It is very important that you master the material that was just taught specifically in this lecture, because we are going to be doing these types of calculations again and again as we go through the acid and base setup. So that is it for me. I hope everybody was able to follow along, and I will see people over in the new chapter for the acid-base equilibrium. Thanks, guys.